and I like to show the MyBots to be used for electrical probing. And here the electrical probing of nanowires. And the work is done by Maximilian Erbeck and Vida Fauske. The work is done in NTNU Nanolab, and the material is provided by the Nanowire group at NTNU in Trondheim in Norway. So a brief outline. I want to give you a motivation of my of the talk, and mainly the motivation for the tool. And then I briefly introduce the nanowires to you. And the main part of the talk will be on how the whole setup is working, how the contacting is working, and what we are actually probing. I will show 3 different types of experiments. The focus lies on the 2-probe, but we will also address the 4-probe and EBID experiments. And I guess my talk will be summarized after about 15 minutes. Okay, so these 3-5 nanowires, these semiconductor nanowires, are promising building blocks for future optoelectronic devices. So think about LEDs or solar cells. And to actually get the structures perfect, you have to be able to measure the electronic properties during your optimized synthesis. So for that we needed a tool, and that's the motivation of my talk here. So the nanowires are small, so we need a probing tool which works on the nanometer scale and in the right environment. In our case, it's a FIP, and it should be easy to operate. We are not people who make probing as our main business. Our main business is to understand these nanowires and make them into devices. And lastly, the structure has to, or the tool has to be flexible, as we are expecting that the structures will evolve, and we need to do following up experiments later. The results I show you are unpublished. So we got our system in February, and where possible, I give you references. Okay, these nanowires, these are compound nanowires of group 3 and group 5 periodic system, and these materials have good electronic property like mobility and direct band gap. And if you want to make them in thin films, you have to always have a matching substrate. Now, the advantage with nanowires is that you can grow them on a lattice mismatch substrate. So we grow gallium arsenide on silicon or on graphene, which gives completely new possibilities. Furthermore, I hope you can see my pointer, you have a design freedom. You can combine different semiconductors together. So we first grow one structure, and then afterwards we switch the conditions and get another composition or another crystal structure or change the doping. We can do that along the nanowire, and as shown on the right, we can do it radially out, so we can make a core shell structure and thereby create novel structures. And the nanowires, the active material, is actually quite small, so we reduce the amount of material we need to use. In our case, the nanowires are grown by molecular beam epitaxy, and it's a vapor-liquid solid mechanism. So on one of the nanowires you see a metallic droplet. So the results I show you here are gallium arsenide nanowires, which are beryllium doped and are grown on silicon. And to give you a feeling for these nanowires, normally the range is between 80 to 300 nanometers in thickness and a few micrometers long. In the results shown here will be 200 nanometers in diameter and about 5-6 micrometers long. Okay, when these structures are so small, you can just see them with the optical microscope, but actually you need to use an SEM to study them. And in the image on the right, we see a small nanowire lying on a silicon oxide substrate. And these big things on the side are the standard probes of the MyBox. So you can get smaller probes, you can maybe reshape them, and then it's possible, as the web page shows an example of, to probe individual nanowires directly. This is, however, not our approach because it's somehow fiddly business. We have an alternative approach that we have the nanowire, here shown in the middle as brown. We connect them to external metallic pads, so gold pads, by using a local deposition made by electron beam induced deposition of platinum. So we weld a contact between the nanowire and the contact pads. To limit the deposition lengths, we have made a tailored substrate which fits the size. This is not so much to increase the speed because its deposition is relatively fast, but to increase the quality of the depositions, the platinum depositions. And then we sprinkle our nanowires on them. These substrates are made by just photolithography with a plastic mask, so quite cheap, straightforward. Here we see 4 gold pads, those contact pads, with in between them nanowires. And now we're picking nanowire by nanowire what we want. So here is shown schematically. We have 4 pads. We have many pads on our substrate. And then with the electron beam, we make a platinum contact to the nanowires. Schematically shown on the left, and on the right, it is shown as in an SEM image. For those who are not familiar with this deposition technique, what we do is we bring from the left, you can see there comes a needle, a nozzle in, which brings a precursor gas close to the surface, and the electron beam, here blue, which you can control in position, breaks up the molecules which come out, or actually it's the secondary electrons which break up these molecules. And the metal part, here shown in red, is deposited behind, and the other parts should fly off. If you now look closely to this deposition, it is not quite pure, and so there are some carbon remains in it. So the conductivity is absolutely not as good as from pure platina or gold deposited by EBL. However, it's a direct deposition method. Further, we have to think that there is a tail, so there could be some deposition outside the main track, which could give conductivity. So what we are after, what we want to measure, is the IV characteristics of many nanowires. So it has to be a quick method. And if we have this IV characteristic, we can deduce with some models the dopant concentration. So in this case, schematically shown here, we have the brown nanowire, and on both sides we have a platina metal contact. So in the middle we have the resistivity of the nanowire. on both sides we have the resistivity of the deposit we made, and then the actual Schottky contact is like a diode, and there is possibly a shunting over it. If we now measure the IV curve, it's such a curly shape with linear parts and exponentially decaying parts. By taking some assumptions, you have to see the reference there. We can deduce the dopant concentration. In the present setup, we do this within a dual beam FIP. We have 3 MIBOTs, and then in the middle you see the substrate, the checkered board with all those contacts on which the nanowires are sprinkled. And then we can select pad by pad, just how we want to have it. And it's no problem to land 3 MIBOTs on the same pad, and we can, for example, test in this configuration if the metal deposited is of the right quality, or we can measure the current going between 2 pads. So this should be an open circuit before we make the contacts with platina. And then from the MIBOTs, the leads go out via to the outside of the vacuum chamber, to a source and to a control unit and logging unit. That's quite standard setup. Some examples of these 2-probe results. So I told you the deposition you make within the FIP or by the electron beam is depending on the conditions you use, so how fast you do it and what voltage you are using and what current. So now you could just draw a platina line between 2 contacts and measure the IV curve of this material you have made, and you can see it's behaving ohmic like, but the resistivity is relatively high. So the setup gives you a quick testing field to optimize your contacts, your depositing conditions. We were after contacting nanowires, so we find the nanowire, make the contacts, and measure the IV curve. In the middle it shows one of those IV curves, and then we can do it again in a larger range. And then later we analyze these curves to find the system resistivity or the dopant degree of our nanowires. And we can do that with many nanowires. So here's another nanowire, and we can also use the MIBOT to afterwards, shown here in the middle. We scrape off or break with the MIBOT the nanowire, and to see that we have an open contact, so that shunting is not a big issue. The 2 points setup is quite easy, but the model behind it has some assumptions. So it's better to take a 4-point probe setup, whereby you could get rid of the contact resistance. And here it's shown symmetrically. We have a nanowire, and we draw with the electron beam 4 contacts to it, 2 for the voltage, 2 for the current, and then we place our probe on it, our 4 probes. But as I told you, our probes, we only had 3 MIBOTs at the start. So we replaced them on the stage slightly, and we used the OmniProbe, the lift-out finger, to take out TM samples as 4th probe. This has some issues. For example, we have to raise the sample so that the MIBOT and the lift-out finger could not crash. And this is shown here. So from the left, you see coming in the bright one. That is actually the OmniProbe, which we can position on one pad, and then the 3 MyBots. And and before that, we have contacted 1 nanowire with 4 electrodes. So, and then through the feed-through, and we have a control unit and a source, as you would have with a bigger setup. And then you can do the experiments. So in principle, this could work fine. However, there are some issues. And the lift-out finger is actually a long arm of about 1 meter, which sticks outside of the vacuum chamber, and is then very prone to vibrations. Furthermore, you can see that by lifting the sample, the MyBot needle comes a little bit horizontal, and thereby not the tip necessarily, but more a little bit back of the probe makes contact to the pad. So if we, for example, put the lift-out finger and a MyBot on one gold pad, we should measure a short circuit, but we could not reproduce that. The simple solution, and we want to have it simple, is to work with 4 MyBots on the same stage, and you don't need, as the pads are quite big, you don't need to use a FIP, but you could also use an optical microscope to place your 4 probes on that. So what is ongoing work is to use actually the fact that you are working in an SEM, and when the electron beam is scanning over the sample, the carriers are introduced, and they could give rise to a current. And the current near the depletion layer, so at both contacts, will be very high, and we can measure this. So we take first, when we're taking a secondary electron image, and at the same time, from the same position, we record the current which goes through the MyBot circuit, and here it's overlaid. We can actually see the extent of the depletion layer, and we can get out the dynamics of the carriers in that region. These are actually very important for the models we use in the 2-probe setup. Okay, my conclusions for the system. So the system allows us to probe a single nanowire quickly, and many of them. And for this batch, actually we find one value of 1.1 10 to the 18th per cube centimeter dopant concentration, and that's then a feedback the growers can have. And regarding the system is for us at exactly the right scale, and it is inside the SEM and the FIP. The operation is really intuitively simple, so we can concentrate on our IV curves and our deposition, not on handling the probes. And because you can combine up to 4 probes very precisely within SEM FIP, which has own complementary possibilities, we have a very flexible system. At the end, I would like to thank the nanowire group at NTNU, the growers for the wires, and the device people for the EBL reference samples they made for us. I want to thank NTNU Nanolab for getting the system and giving us the freedom to play with it and see what is possible with it. And I would like to thank Imina Technology for advice before and after the experiments. And I want to thank you all for tuning in and listening.